Hello friends, how are you wherever you are? Once again, I'm Erisa, coming back to teach you some curriculars. In our first lesson about curriculars, we introduced integration and we basically talked about integrating powers of x, limits of integration, and the polynomials. So in today's lesson, that's the second lesson about integration, we want to talk about the integration of sines, cosines, integration of exponential functions, and then move on with integration. Okay. Dear friends, we said last time that if you want to understand integration, then you must really know differentiation, because integration is the reverse process of differentiation. Now, today we want to talk about integration of sin x and the cos x. But for us to be able to understand these integrals of sin x and cos x, we have to first go back to differentiation. Okay, this is what you know about the derivative of sin x. If I differentiate with respect to x, sine of x, the derivative of a sine is a cosine of x. Okay, now this means that if I integrate cosine of x with respect to x, it takes me back to what I differentiated, which is a sine of x plus a constant of integration. Remember, we add this constant of integration because they are some constants which disappear or which goes to zero when we differentiate. So when you integrate, those constants come back. Okay, unless you have further information about the integral, that's when you can go on and evaluate the value of c. Otherwise, if you don't have the limits of integration, do not try to attempt the value of c. Okay, yeah, so c can only be obtained if we have further information about the integral. But always add a constant of integration whenever you are integrating indefinitely. Okay, so let's look at this. If you differentiate cosine x, the derivative of a cosine is negative sine x. So what does it mean? If we are to integrate a negative sine of x with respect to x, then it takes us back to what we differentiated, which is the cosine of x. But, they may not give you with a negative. What if we factor out that negative? This is the same thing as an integral, okay, with a negative 1 outside. I can put a negative 1 and write sine x by dx, okay? This still will be cosine of x because we have not changed anything, okay, plus sc. Now, if I divide through by a negative 1, it means that the integral of a sine x by dx, it will be negative cosine of x plus a constant. I'm dividing through by negative 1. So if I divide this through by negative 1, still it gives me another constant. So I just call it constant c. So don't say now what happens. At this stage, we had plus a constant. Okay, then again this stage we are saying plus the same constant. No, this is a constant. It can be negative, very positive. We divided it through by negative 1, so that is c divided by negative 1 it still gives you another constant. Therefore it's plus a c. That should not bother you so much. So what are we learning so far? We are discovering that the integral of a cosine x by dx is a positive sine x plus sc, and the integral of a sine x by dx is a negative cosine of x plus sc. These results are so important as we discuss this concept of integration. These results are really going to be so important. So you make sure you highlight them in your notebook, because later on, as we try to handle integration, as a complicated, this can appear as a complicated part of integration over an integral. So we shall be able to remember that when we integrated a cosine, we ended up with a sine. And when you integrated a sine, we end up with a cosine. By the way, what we get here is the reverse of what we get when we differentiate, because differentiating a cosine gives you a negative sign, okay? And here, integrating a sine gives us negative cosine, okay? So don't confuse those two results. Don't think that when I integrate a sine, I'm gonna get, a positive cosine. And when I integrate a cosine, no, integration must be understood from differentiation. The moment you understand differentiation, integration is a walkover, because we have defined it as a reverse process of differentiation. So that's what we are doing basically. Okay, let's move on. Maybe just work out a few examples about this, but still, basically there's nothing so much to discuss here, because it is coming ahead when we are discussing function of a function or function of any function of x. These functions will be popping in. Okay. Next, let's talk about exponential functions. Exponential functions. We first understand what an exponential function is, and then we go ahead to integrate exponential functions. Friends, so many times we meet these exponential functions. Okay, they have a very wide application in engineering. But what is an exponential function? A function of the form, which is the form a to power u, where a is a positive constant and u, a variable, is called an exponential function. Okay, so if you have a function of the form a to power u, where u is a positive constant, for example, okay, if I have a function which is 3 to power x, that is an exponential function. 3 is a positive constant, which is the base, and the power u is a variable here, which is x. Okay, if I have e to power 2x, that is an exponential function. If I have 5 to power Cosx, all those are exponential functions. But people think that only e to power x is an exponential function. No, that is just one of the exponential functions. Okay, it is actually the most important class which people use frequently. E is a natural base, which is about 2.7, 1 something. If you compute your calculator, you get E as 2.7 something. That is a natural base. So when we talk about exponential functions, basically the most important functions of our interest are e to power x, but all these are exponential functions. Don't forget about them. We can also integrate them as exponential functions. Okay, now having discovered what an exponential function, okay, is, how do we integrate exponential functions? Okay, I want to talk about the integration of exponential functions. How are exponential functions integrated? Remember, okay, I have told you that if you are to understand integration, you must always refer to differentiation, because you are performing the reverse process. Okay, if you know how to drive a car and you can drive it forward perfectly, okay, when you are driving back, you have to refer to the forward driving. Okay, where do I find the reverse gear? So it is a reference to the forward gears. So you have to understand differentiation if you are to master integration. That will always be a point of emphasis as I take you through this area of integration. Okay, let's see how do we integrate exponential functions. We know that when you differentiate e to power x by dx, you end up with the e to power x. The reason why we end up with the same thing is that we always differentiate this power and multiply by, e to power x. Okay, the principle of differentiating exponentials of this class e to power x is write what they have given you to differentiate and multiply by the derivative of the power. So here, the derivative of x is 1. So if I multiply through by 1 here, it does not change, it remains e to power x. So what does it mean? This means that if I integrate e to power x by dx, it takes me back to what I differentiated, which was e to power x, okay, plus a constant. C is any other constant, okay, which when added to this function before the process of differentiation disappears to 0 after differentiation. So always add a constant of integration if you don't have limits of integration, or if you don't have any more information that enables you to find the value of C. Okay, so let us generalize this, because sometimes when you use e to power x and now you bring in e to power 3x or e to power cos x, students tend to get confused. Okay, so let's generalize it with a result u. Okay, so I have d by dx of e to power u. Okay, in this case, u can be anything. Okay, u can be 3x, it can be x minus 1, it can be any variable. Okay, so it's going to be e to power u. So the integral of e to power u by du is equal to e to power u plus a constant. Okay, so let's see the relevance of using u instead of x. Now, what if I was given this? I was given to differentiate e to power 5x by dx. Okay, differentiate e to power 5x. What do we get? We end up with e to power 5x, but we multiply by the derivative of the power. So what does it mean if I'm to integrate e to power 5x? Okay, let me first put a 5 here, okay, to cater for this 5, and this is going to be e to power 5x plus a c. So the next step, okay, divide through by 5, e to power 5x is 1 over 5 of e to power 5x plus c over 5, but still that is a constant. Okay, so that's the relevance of using u at this stage. Okay, so whenever you bring in anything else or any other variable, or u here is simply standing for any function. Okay, e to power any function where I'm calling it u. So when you differentiate and try to integrate, it will be easier for you because you're performing the reverse process. So let's work out just a few examples here. Remember, this is coming ahead. We are, touching the sensitive parts of integration before we now piece it out together, piece it up together, and come up with something. You will see when we get there. Okay, so let's try this out. The first one, I call this number 1, this is 2, and this is 3. So the solution is 1. They're asking us to integrate e to power 2x by dx. Okay, don't even waste time. Much as we have a formula coming ahead when we discuss what we call change of variables, but here the shortcut is write e to power 2x. Okay, then come back here and differentiate this power. When I differentiate 2x, I get 2. Okay, or here we don't, oh, sorry about that. We don't multiply, but we divide. Okay, you divide by 2. Divide by 2. Then plus constant of integration. Simply that is it. Okay, 2. When we integrate e to power x plus 1 over e to power x by dx, this is the same thing as integrating e to power x plus e to power minus x, just using the rules of indices. Okay, and this will be e to power x plus e to power minus x. But we said you differentiate the power and divide by that derivative. So this is a 1, this is a negative 1 plus a c. Okay, so in the end, we shall have e to power x minus 1 over e to power x plus a c. And we are done with 2. So the third is integral from 0 to 1 plus e to power minus x over 2 by dx. Okay, integrate this. This is, if you integrate 1 with respect to x, you get x. Okay, plus, remember there is this a half, then we want to integrate e to power minus x. Okay, we say differentiate the power and divide by the derivative you get. And if you have limits of integration, do not add a constant. It will just be a waste of time. Okay, so this is the same thing as 1 minus e to power negative 1 over 2. Okay, then minus lower limit, which is 0 minus a half of e to power 0. Okay, a number to power 0, we know it is 1. So this is going to be 1 minus, okay, 1 over 2e, then plus a half. Okay, and therefore we have 3 over 2 minus 1 over 2e. Or if you are too much of a person who wants to factorize, minus 1 over e. And that's the answer. So, having come up with the building blocks of integration, okay, we now want to begin serious work. We want to talk about functions of a linear function of x. To discuss these integrals of functions of linear functions of x, we bring in what we call a change of variables. Okay, we want to see an example. Suppose you have been given this integral. Okay, we want you to integrate 5x minus a 7 to the power 6 by dx. Okay, one of the ways of approaching this integral is to expand, okay, 5x minus 7 to the power 6, but it's a long way because you have to go the Pascal's triangle or use binomial coefficients, whatever you want, and it is going to take too much time. So what do we do? Okay, here the best method is to substitute. Let 5x minus 7 be represented by u. Okay, so here the integral changes, but before you change the integral, you also have to change the variable dx and it becomes du. So you know that if I differentiate 5x minus 7 to the same thing as differentiating u with respect to x, okay, and here I get 5 will be equal to du by dx. Okay, so what does it mean? If you want to make dx the subject, it will be 1 over 5 of du. So we are going to substitute. Okay, it will mean that the integral of 5x minus 7 to the power 6 with respect to x now changes the integral of u to power 6. Then dx is now du over 5. Okay, what do you get? Okay, when you integrate u to power 6, you get u to power 7 over 7 plus a constant of integration. We now substitute. What is our u? U is 5x minus 7 to the power 7. Okay, sorry about that. This is to the power 7 over 7 plus a constant of integration. That is the integral of 5x minus 7 to the power 6. So that's the answer. So it has saved us a lot of work expanding that function, coming up with lots of coefficients and powers, then looking at it as a polynomial. Okay, the knowledge of functions of a linear function of x. Why do we say functions of a linear function of x? This is a linear function of x. Okay, now we are calling it u here, and now u, we're integrating u to power 6, but u is a function of a linear function. Okay, so that's how we approach these integrals. Now, friends, I don't want to make these videos to be a bit long. First of all, it becomes boring to watch and learn. Okay, when you are watching a long video, remember, this is an online program where you're not, it's not a one-on-one with the teacher. You don't have that physical contact with the teacher. But we try to engage you so you can learn. So if I make a lengthy kind of video, it affects the learning towards the end. Some students tend to withdraw. So I'm going to continue with the functions of linear function of x in my third lesson about integration. So wait for what is coming ahead. Okay, hope you stay safe, you learn this information. I believe it is going to help you. All right, have a nice day.